Usually, when we talk about a medical diagnosis, there's this expectation of pure visible precision. You break your arm, the x-ray shows that jagged white line, and the doctor just points directly to it.
Right, it's very binary, broken or not broken. I mean, we inherently crave that kind of visual confirmation because it allows us to just categorize a problem and instantly move on to a solution.
Yeah, exactly. But then you step into the world of healthcare mathematics, and suddenly that x-ray machine is completely useless.
Oh, totally useless.
The danger is completely invisible. We're suddenly looking at this landscape of numbers that is, well, murky and just full of hidden traps. So today's mission on the deep dive is decoding a fascinating, highly specific competency bundle known in the testing world as time, money, and measurement math.
And, that title might sound like a middle school syllabus, but the stakes literally couldn't be higher here. We're exploring a really critical set of real-world skills.
Not just passing a test.
Exactly, not just a test. These are the calculations that govern everything from, say, a nurse catching a potentially lethal medication error on a really chaotic ward, all the way to you, the consumer, figuring out if a massive blowout sale at the mall is actually just a psychological math trap.
Right, because the core of this whole deep dive boils down to one specific question that entrance exams like the TEAS or the HESI are trying to answer, and that is, can a person move fluidly between real-world numbers without a calculator, and crucially, without making a fatal cognitive error?
Yeah, because a mistake here isn't just a red mark on a test paper. It has actual physical consequence.
It really does.
It tests psychological agility just as much as mathematical ability. And I think to understand why this is so critical, we have to look back at the crisis that basically forced educators to realize traditional math testing was failing them.
Oh, right, the dropout crisis.
Yeah, in the late 1980s and 1990s, nursing schools across the country realized their students were dropping out at just alarming rates.
Which is why.
It is. And when administrators dug into the data, they discovered these students actually possessed immense clinical knowledge. They had the empathy required to heal.
But they were hitting a wall.
They were hitting a massive wall because of weak foundational academic skills.
Right, so imagine spending thousands of dollars on tuition, getting midway through a high-stress clinical rotation, and then failing out because of fractions. Okay, let's unpack this, because test makers and nursing educators actively debate what this math even is, right?
They do.
I mean, some argue it's just basic arithmetic dressed up in a word problem, but others argue it is an entirely distinct cognitive skill known as quantitative literacy, or numeracy.
And that distinction is vital. Abstract math ability is really just doing arithmetic in a vacuum. Numeracy, on the other hand, requires translating an ambiguous, messy, real-world scenario into a solvable equation before any arithmetic even happens.
Right.
I mean, standard algebra where you just solve for x is sort of like memorizing vocabulary words in a quiet room with flashcards.
Right. Well, numeracy is like trying to translate and speak a foreign language in the middle of a loud emergency room.
Exactly.
The patient's IV is dripping at 30 drops a minute. The tubing has a specific drop factor. Alarms are blaring. A doctor is yelling for a different medication. You have to filter out all that noise, translate that chaotic reality into a math problem, and only then do you actually do the math.
Yeah, and to stop those massive attrition rates, the industry realized they had to create a gatekeeper. So organizations like Health Education Systems, Inc., or HESI, which was founded in 1988, and Assessment Technologies Institute, ATI, in 1997, they built these admissions readiness exams.
But they didn't invent new math, right?
No, not at all. They just imported existing arithmetic, but heavily emphasized real-world scenarios.
Because the exams couldn't just ask for, like, the square root of 64. They had to prove the questions actually measured the skills required for the profession.
What test makers call construct validity.
Construct validity, right. So you might have to read a picture of a partially filled syringe or interpret a confusing pay stub. And these real-world scenarios basically rest on three core pillars: time, money, and measurement.
Yeah.
Let's start with that first one. Time leans heavily on the 24-hour clock.
Right, which most civilians just call military time. That actually traces back to the U.S. Armed Forces formally adopting it in 1920.
Because of ambiguity.
Right, exactly. If you're coordinating a massive troop movement, saying 6.0 is dangerously ambiguous. I mean, is it dawn or is it dusk? The 12-hour clock creates this structural vulnerability in communication strictly because it reuses the exact same numbers twice a day.
And hospitals obviously saw that vulnerability. They realized an AM/PM transcription error on, say, a cardiac medication order could literally kill someone.
Oh, absolutely.
But navigating a 24-hour clock is where people completely trip up on these exams. And it's specifically because of the cognitive friction of crossing midnight.
Yes, the midnight trap.
Let's say you have a patient who is NPO, nothing by mouth. The order says they are NPO starting at 23:59, which is 1 minute to midnight.
Right.
And their surgery is the next day at 11:30 in the morning. How long have they been fasting?
Well, see, our brains inherently want to subtract the smaller number from the larger number. That's just how we're wired.
Right. So if you take 23:59 and subtract 11:30, you get 12 hours and 29 minutes.
Which is mathematically possible on a piece of paper, sure, but chronologically, it is nonsensical.
Totally nonsensical.
You're basically trying to do linear math on a circular concept. When you cross midnight, the day resets. You have to add a full 24 hours to your end time before you subtract the start time.
And if a clinician gets that elapsed time calculation wrong, the patient is either starved for entirely too long or, and this is worse, the anesthesiologist puts them under thinking their stomach is empty when it actually isn't.
Which creates a massive aspiration risk during surgery.
Yeah, it's terrifying.
The precision required there is totally non-negotiable. And what's fascinating here is how that illusion of simplicity, where the math looks easy on the surface but hides this deep logical trap, is exactly what drives the second area. Monetary calculations.
Oh, consumer math.
Yes, this deeply explores the psychology of how we spend money.
We see this every single day with unit rate comparisons. Like, you're standing in the grocery store aisle, you see a 12-ounce bottle of shampoo for $3.60. Next to it is a 16-ounce bottle for $4.80. Most of us just instinctively grab the bigger one.
Right, because we've been completely conditioned to believe that bulk is always cheaper.
Economies of scale, right?
Exactly, and retailers completely rely on that assumption. We just outsource the math to our assumptions instead of our calculators. But if you take a second to actually do the division, so $3.60 divided by 12 and $4.80 divided by 16, they both come out to exactly 30 cents an ounce.
You aren't saving a single penny by buying in bulk.
Not one penny. The exam tests if you can override that psychological bias and actually calculate the comparable rate.
I have to say, my absolute favorite trap in this section is the sequential percentage discount.
Oh, that one gets everyone.
It really does. Imagine you find a jacket for $100. The sign says it's 30% off. You get to the register and the cashier smiles and says, hey, you get an extra 20% off today.
Such a good feeling.
Right. Our brains use what psychologists call fast thinking. We add the 30 and the 20, get 50, and assume the jacket is half off.
Because the human brain vastly prefers to add rather than to calculate compound percentages. Addition just takes way less cognitive energy.
Yeah, but the order of operations changes the reality entirely. You take 30% off the initial $100, which brings the price down to $70.
Right.
That second discount, the extra 20%, doesn't apply to the original 100. It applies to the new $70 price tag. And 20% of 70 is 14. So you subtract 14 from 70 and you pay $56.
It's a 44% total discount, not 50%.
Exactly. The retailer successfully makes you feel like you are getting this massive steal while mathematically protecting their profit margin.
It's brilliant on their part. And test makers love sequential discounts because they reveal whether a student actually understands the underlying logic of the operations rather than just passively letting their brain add the two biggest numbers in the sentence.
Right. It's about the logic. And here's where it gets really interesting, because that same requirement, understanding the underlying logic instead of just moving numbers around, forms the backbone of the third and honestly most critical domain: measurement and dimensional analysis.
Yeah, this is the skill that maps directly onto drug dosing. And to really understand the mechanism behind it, we kind of have to trace the metric system back to the French Academy of Sciences in 1795.
I love a good historical tangent.
That's a great one. The Academy defined the meter as 1/10,000,000th of the distance from the North Pole to the equator. Yeah, it was part of this whole post-revolutionary push for a rational, universal, decimal-based system. They desperately needed to replace the chaotic patchwork of local units used across France. I mean, back then, a pound of flour in one village meant something completely different in a village just 10 miles away.
That sounds like a nightmare for trade.
A total nightmare. And medicine universally adopted this metric system, milligrams, milliliters, specifically because its base 10 structure minimizes calculation errors. Decimals just shift left or right.
But the thing is, clinicians in the United States don't just work in the metric system.
No, they go.
They have to convert measurements constantly, and they use a process called dimensional analysis, which is also known as the factor label method. Let's actually look at a concrete example from the source material.
Okay, let's do it.
So a physician orders a medication dose of 5 milligrams for every kilogram of a patient's body weight. The patient steps on the scale, and it reads 154 pounds.
Right, so step one requires converting those customary pounds into metric kilograms. You divide 154 by 2.2, giving you 70 kilograms.
Got it.
Then step two, you multiply that 70 kilogram weight by the ordered dose of 5 milligrams per kilogram. That results in a 350 milligram total dose.
Okay, that makes sense.
But drugs rarely exist as just pure dust.
Right.
They usually come suspended in a liquid vial. And the vial in this scenario has a concentration of 250 milligrams in every 5 milliliters of liquid.
So you have to figure out how much liquid actually goes into the syringe.
Exactly. And dimensional analysis is how you solve it. You basically set up a sequence of fractions. You start with what you need, which is 350 milligrams.
Okay.
You multiply that by a fraction representing the vial. So 5 milliliters on top, 250 milligrams on the bottom. And the brilliance here isn't the arithmetic, it's the words.
Labels.
Right, the word milligram is on the top of your first number and the bottom of your fraction. So they cancel each other out. You are left with only one unit, milliliters. Yeah, so then you just multiply 350 by 5 divided by 250 and you get 7 milliliters.
It's kind of like doing currency exchange at an airport before the euro existed.
That's a great way to think about it.
Like you have dollars and you want to buy a croissant in Paris. You can't just hand them dollars. You have to trade dollars for francs and then trade francs for the croissant. If you set the exchange rate up backward and try to multiply dollars by dollars, you don't end up with a pastry.
No, you don't.
You end up with dollars squared, which makes absolutely no sense.
Right. The units themselves guide the math. If the words don't cancel out cleanly, the mathematical structure basically collapses, algebraically flagging your mistake before you ever touch a patient.
It's like a built-in safety net.
Exactly. It forces the clinician to verify their logic before calculating the final number, because a major trap on entrance exams is assuming all conversions are equal.
Which they aren't.
Not at all. Metric-to-metric conversions, like grams to milligrams, just require moving a decimal point. But customary-to-metric conversions, like pounds to kilograms, require actual multiplication factors.
Right.
Treating a pound-to-kilogram conversion like a simple decimal shift will drastically underdose or overdose a patient.
Now, that elegantly structured unit-canceling system works beautifully in a classroom setting. But highly trained professionals still get these conversions wrong in the real world, right?
They really do. And the most famous example of a unit conversion failure actually happened in space, not a hospital.
Oh, the NASA story.
Yes. In September 1999, NASA lost the Mars Climate Orbiter, which was a spacecraft that cost over $327 million.
Unbelievable.
It literally burned up in the Martian atmosphere, all because of a communication failure regarding units.
Basically, two different teams assuming they were speaking the exact same mathematical language.
Exactly.
Yeah.
An engineering team in Colorado was calculating thruster data using pound-force-seconds, which is a customary unit. But NASA's navigation team in California assumed the values they were receiving were in the metric standard, Newton seconds.
And it wasn't just a typo.
No, it was a fundamental assumption about the units that went completely unchecked for 9 months of flight. That mismatch slowly built up a navigation error over the entire journey to Mars. It proves that unit conversion mistakes happen to world-class professionals, and the results can be just catastrophic.
I mean, a lost satellite is a massive financial disaster, but in healthcare, a mathematical mismatch costs human lives. The Institute for Safe Medication Practices, or ISMP, closely tracks these incidents.
It do.
And they document a recurring nightmare known informally as the decimal point error.
Yeah, this is terrifying. A single misplaced decimal point, or even a smudged trailing zero, can turn an intended dose into one that is 10-fold or 1,000-fold too large.
1,000.
Yes. Imagine a tired nurse on hour 11 of a shift. The brain is fatigued. It relies on pattern recognition rather than deep analysis. If an order says 5.0 milligrams and the decimal point is faint or, smudged by a pen mark, the brain instantly processes it as 50 milligrams.
Which is exactly why the entrance exams in hospitals universally mandate incredibly strict formatting rules. You must always use a leading zero before a decimal.
Always.
It is point 0.5, never just point 0.5. That leading zero basically acts as a visual stop sign. It forces the tired brain to pause and recognize the decibel.
And you must also never use a trailing zero. It is 5, never 5.0.
Right.
And I think it's important to realize these aren't just nitpicky grammar rules for mathematicians.
Yeah.
They are institutionalized, trauma-informed responses to documented tragedies.
There is another nuance in clinical math that completely defies what we learn in elementary school, and that's rounding.
Oh, yes.
If we calculate 2.5, we are normally taught to round up to 3. But in specialties like pediatrics or oncology, where drugs are highly toxic or patient bodies are very small, nurses often have to do something called truncating.
Right. Truncating means completely ignoring the normal rounding rules. You literally chop off the decimal and round down.
Just drop it.
Yes. If a pediatric calculation comes out to 4.8 milligrams and the absolute safety ceiling for that child is 4.8, rounding up to 5 pushes them into toxicity.
Wow. So you truncate to 4.
Exactly.
Yeah.
The exams test whether you can override your basic arithmetic instinct and follow the specific safety parameters of that exact scenario.
I have to admit, hearing all of this makes me wonder about modern technology. I mean, we live in an era where hospitals have barcode scanners at every bedside, right? And smart intravenous pumps that calculate flow rates automatically.
They do.
So why do we force nursing students to solve dimensional analysis by hand on an entrance exam? Why can't they just use a calculator?
Well, this raises an important question, and it actually sits at the center of a massive pedagogical debate in nursing education.
I bet.
Yeah, some exam sections allow basic calculators, while others strictly forbid them. The core argument against calculators is that dimensional analysis is a reasoning skill. Educators are really trying to build number sense.
Like having a gut feeling for the math rather than just plugging digits into a screen.
Exactly. If a student lacks the number sense to estimate that a 154-pound person is roughly 70 kilograms, they are entirely at the mercy of their device.
That makes sense.
If they accidentally hit the multiply button instead of divide, and the screen says the patient weighs 338 kilograms, they won't recognize the absurdity of that number. They'll just trust the screen over reality. Technology, like a smart pump, is designed to be a secondary safety net. It cannot replace human numeracy.
So what does this all mean for you, the listener, especially if you have no intention of ever taking a nursing entrance exam? Outsourcing your critical thinking to a screen leaves you vulnerable.
Highly vulnerable.
Without internal number sense, you can't verify if a shift-working parent's overtime pay is actually accurate on a messy pay stub. You can't competently calculate your own child's liquid fever reducer at 2 in the morning, and you definitely can't spot when a retailer's sequential discount is just an illusion.
Right. These exams aren't just arbitrary hurdles. They are enforcing a vital framework for navigating the world. I mean, they prevent clinical errors at the bedside, and they protect consumers from deceptive pricing and their own cognitive shortcuts.
It is really about maintaining a conscious grip on the numbers that dictate our reality.
And if we connect this to the bigger picture, there is a lingering, almost tragic systemic issue hidden in the source material.
Oh, yeah, the metric system.
Yes, the United States has never fully converted to the metric system, setting it apart from almost every other nation on Earth, and that refusal places a uniquely persistent professional burden on American healthcare workers.
Because an engineer in Germany or a nurse in Japan just works in metric, the cognitive load is entirely streamlined.
Right. But American nurses must remain flawlessly fluent in both customary and metric units for their entire career.
Every single day.
Every single shift, they are mentally bridging the gap between the pounds on a patient's bathroom scale and the precise metric milligrams of their life-saving medication. It is an immense cognitive load that literally never goes away, a constant translation between two mathematical languages.
That completely changes how you view the work happening behind the scenes during a hospital stay. And it brings us right back to our original thought. When you look at an X-ray, the broken bone is a comforting visual absolute. But the math keeping that patient safe is a complex, murky landscape of translations, cognitive biases, and hidden decimal traps.
The professionals navigating it are doing constant mental currency exchanges just to keep the structure from collapsing.
It is largely invisible work, but that numeracy holds the safety of the entire healthcare system together. We want to thank you for joining us on this deep dive. The next time you encounter a 24-hour clock or a double discount sign at a department store or the dosage instructions on a medicine bottle, take a moment to look a little closer. Set up your mental currency exchange, trust your number sense over your calculator, and keep questioning the numbers you see in the world around you. Until next time.